I guess we'll go ahead and get started. How's everybody doing? Good? Have a good weekend? You have a question? Okay. The homework is difficult? That's intentional, yes?
Also, I tried to check and the very first problem, I don't think alpha does anything. So either I went crazy or it doesn't do anything.
I'm sorry. I don't remember what the first problem is.
It's like, what if you did official least squares regression, OLS, but you have an alpha? And what I found is the alpha doesn't seem to matter for finding W fast.
I don't remember the exact problem off the top of my head. If it's weighted least squares regression, the matrix A makes a difference. That's for sure. But I'm not sure which problem we're looking at here. Okay. Anything else? We're ready? Ready to go? Okay. So we left off. Can you guys hear me? Am I coming through? Are there even speakers in this room? I don't even know where they are, if there are speakers. But, huh? Those look like air conditioner vents.
No, that looks like right above.
That's not a speaker. That's like an infrared thing. But I hear something coming from somewhere. Okay. Well, anyway, we left off talking about regularization, okay? And we didn't quite finish. But the idea is that in regularization we modify the loss function, okay? So in ordinary least squares regression, we are trying to minimize the sum of squared residuals or the mean squared error. Those are just the same thing, but scaled or factored different by a factor of 1 over n. Okay, and that is this L. But in regularized regression, we insert a term that penalizes complexity. Okay, and we say that maybe you can improve the coefficient estimates. You can improve the fit by changing the coefficient estimates, but that might incur a penalty. Okay, by doing that, and so the coefficients that you estimate will be different from the least squares estimates. Okay, and we talked about this example where, maybe you will prefer to live farther away and have lower rent, or maybe you're going to prefer to live closer and pay a higher rent because you hate commuting or something like that. Okay, and similarly, when we modify the loss function, we can have different values of lambda and different ways to measure the complexity. And we started off here and we said, if we think about what a fourth order and fifth order polynomial look like, okay, the fit is exactly the same. It's just that we've forced, for the fourth order polynomial, we've forced that this coefficient for w on the fifth order term has to be 0. Okay, and so measuring complexity, we can kind of measure how many of our coefficients are 0 or not 0. Okay, and that would be using our L0 norm. But unfortunately, using the L0 norm is almost impossible to solve computationally, because it just computationally requires is too intense if you have a high number of predictors. And so things can get better if we use the L1 norm, which says we measure our complexity in terms of the absolute values of the coefficients. Now this feels a little strange, okay, because it seems like, well, why should, just because the coefficients are bigger, why should that incur a greater penalty? And what does the size of the coefficient have really anything to do with the complexity of the model? But it actually does work out, especially if you scale your input data. Okay, if you kind of scale all of your input data so that everything is normalized, everything is kind of on a range of -2 to +2 or -3 to +3, where everything has a mean of 0 and standard deviation of 1, certainly using something like lasso, okay, where you use the L1 norm and using the absolute value of the coefficient as a measure of complexity can work in terms of reducing the variance that we see in our model, okay? And then the other alternative for modifying our loss function is using the L2 norm, or using the squares of the coefficients, okay? So right now this has all been described in an abstract sense, and I'll show you a bunch of graphs, and maybe it will help, maybe it won't. We'll see, okay? Like I try to illustrate these things, and depending on who you are and how you learn, some of these visual graphs may be helpful, and in other cases they're not as helpful, and just the word descriptions are better. And so I'll show them. You know, I thought they were helpful, and that's why I'm going to share them with you. But if you don't find them helpful, that's also okay. All right. So the L1 norm, when we use that, the absolute values of our coefficients, that's called the lasso. And when we use the squares of the coefficients, that is known as ridge regression. In both of these things, we incur the least amount of penalty when our coefficients are 0. Okay, when the coefficients in our model is 0, that's going to incur no penalty, right? If you think about lasso and if you think about ridge, okay, what ridge regression does, because it's using the squares of the coefficients, it's saying, I really, really, really hate when the coefficients get really big. Okay, I really hate big coefficients. That's what ridge regression says, okay? Because if your coefficient is size 1, 1 squared is only 1, and ridge regression goes, I'm not a huge fan. It incurs some penalty, but the penalty is only 1. However, if the coefficient goes up to size 10, and you square 10, then it's 100, right? And so ridge regression is going to say, I hate this coefficient a lot, okay? Because it's much bigger, right? 10 squared is 100, whereas 1 squared is only 1, okay? Over here with lasso, when you're using the absolute value of the coefficients, lasso is just grumpy and it hates all coefficients, and it doesn't matter if it's big or small, okay? 10 incurs a penalty of 10, and it doesn't care if the coefficient goes from 10 to 11. That's even worse. 11 is worse than 10, but 2 is equally worse than 1, okay? So going from 1 to 2 incurs an additional penalty. Going from 10 to 11 incurs the same amount of penalty in lasso regression, okay? And so lasso is really only pleased when it reaches down to 0. Whereas with ridge regression, going from 10 to 11 increases the penalty quite a bit, going from 100 to 121. Going from 1 to 2 increases the penalty a little bit, going from 1 to 4, but the amount is bad. And pushing it down towards 0, again, will decrease the penalty, but you know, once you get smaller than 1, the amount of improvement, you know, gets less and less and less. Yeah, question?
What's the, like, in which situation would you use which?
Yeah, in which situation would you use which? We'll talk about that. So one of the side effects, okay, of the difference between lasso and ridge regression is that lasso can end up being used for variable selection. It's going to push some of these coefficients down to 0. In ridge regression, it rarely pushes any of the coefficients down all the way to 0. It might push them down to be small, but you're much more likely to get a bunch of coefficients that are decimal points than any coefficient to be 0, okay? And so, you know, we'll see some of this in the things, okay? So here's a little example here, okay? And so the true relationship, so this is the true relationship between z and x. I've got x1 and x2, okay? And z, the true z here, is going to be 1.5 times x1 plus 0.5 x2, okay? And then I add some random noise to this, okay? And I fit a linear model here, okay, and it estimates the coefficient to be 1.45 and 0.45, okay, and we know that the true coefficients are 1.5 and 0.5. Okay, is that right? What I can do is I can use this function called optim, okay? So the function optim will find the values, or the kind of the parameters that will minimize whatever function you're trying to do, okay? So here I tell it the function that we want to optimize, this is called OLS loss op, is going to be basically what I've plugged in here is the sum of squares residuals. Maybe I should add some more text to these slides here, okay? So LM already finds the coefficients that minimize the sum of squares residuals. Here, I've written my own loss function, okay? And this loss function calculates the sum of squares residuals, okay? And R's function optim, you can plug in any kind of function into it, okay? And it will find the values that will minimize the function. Okay, and so in this case, OLS loss is a function of the data that we have plus the coefficients W1 and W2. Okay, and so when I plug this into R's function optim, I started off at 0, 0, and it finds and it searches, and it says, you know, the W1 and W2 that will minimize the sum of squared residuals, which is what OLS returns, is going to be 1.4588833 and 0.4533399, which is exactly the same, or pretty much exactly the same as these values here, just off by some machine error. Yeah.
Why is that?
Uh-huh.
For the lim function,
why is 0 plus x1? Why is it 0 plus x1 x2? In LM, R's LM function, if you don't include the 0 plus, then it will try to fit an intercept term. Okay, and so to kind of keep things simple, I didn't include a 0. I didn't include an intercept, or my intercept here is 0, and so LM, if you put in 0, will tell R don't fit an intercept. Okay, just estimate your W1 and W2. Okay. So anyway, telling R to use optim to minimize the sum of squared residuals works here. Okay, and this will allow me to fit kind of in a manual way, not really manual, but kind of see how modifying the loss function will change our coefficient estimates. Okay, and so here, the OLS loss, again, what we're doing is we just take in our coefficients W1 and W2, and I create my W matrix and X matrix, and I do Z minus XW transpose times Z minus XW, right? And that's going to be our sum of squared residuals. Is that okay, that we see that this returns the sum of squared residuals here? Okay, and so this is just code to get it to plot, okay? All right, so this is here just so in case you want to plot it. And so here, this is a contour plot, and this shows the values of W1 and W2 that will minimize the sum of squared residuals. And we can see that it's in this paraboloid bowl shape, and that the optim happens, you know, close to 0.5 and 1.5, but it's a little bit different because of, you know, the noise that we've observed in our data. All right, and so this is what the contour plot looks like for the ordinary least squares. Okay, so if we're trying to minimize the sum of squared residuals, it looks like a paraboloid. And so, you know, if you have other things in here, you're not going to get the smallest possible residuals, but, you know, it will be off by a bit, okay? Okay, so this is the L1 penalty, okay? So the L1, this is what we use for lasso. All we're doing is we're taking the regular OLS loss. This returns the sum of squared residuals, right? This is the sum of squared residuals. and we take the absolute values, the sum of the absolute values of our W coefficients. Okay, and so so this is the lambda. Okay, and we multiply it by lambda times the sum of the absolute values of our coefficients W1 and W2. All right, so does that make sense? So take a look at this. This OLS loss is the sum of squared residuals, and this is the lambda times the sum of the absolute values of W1 and W2. So this is exactly equivalent to what we have here. Okay, this is the lasso penalty. L is just the ordinary least squares, sum of squares residuals, which we have back here. Okay, I don't have the 1 over n term. Okay, but I have t minus xw or z minus xw transpose t minus xw, z minus xw. Okay, and now I'm doing lambda times the W1 norm, okay, or the L1 norm of W, okay, which is right here, okay, lambda times the sum of the absolute values of W1 and W2. And then I use, I have it optimize, okay, and I tell R optimize the L1 loss, okay, and so when I do this, the OLS, the least squares estimates, the coefficients that maximize or minimize the sum of squared residuals are 1.458 and 0.453397. And here we can see what using different values of lambda do to the coefficients here. Okay, so if I use lambda equals to 10, what happens? This pushes 1.458 down to 1.436 and 0.453 down to 0.43. If I increase lambda to 50, this gets smaller, and this also gets smaller. And if I increase lambda to 100, this also gets smaller, and this also gets smaller. Okay, so increasing lambda pushes down both the W1 coefficient and the W2 coefficient. All right. And if I keep increasing my lambda, this W1 coefficient keeps getting smaller until here at lambda equals 500. Okay, so at lambda 300, this one's almost 0, this one's around 0.595, and at lambda 500, both of these coefficients are pretty close to 0, okay? Because at this point, with lambda 500, we're saying, we're saying the penalty of increasing W is very big. We're doing 500 times whatever our coefficients are, okay? And we're also trying to minimize our sum of squared residuals, which at this point, it's just better to go with 0 W's, okay? W's that are 0, because changing that will increase our penalty here. Okay. This is, here is the kind of the plot here. This red dot is the W1 and W2 that minimize the OLS regression. And watch what happens. So this is with lambda equal to 10. The coefficient estimates are similar, but a little bit different. Okay? These blue lines represent if W1 and W2 are both 0. Okay? And as I increase lambda, notice what happens to the behavior of this blue dot. Okay? And also the contour lines will also change. Okay? So this blue dot will move down, and it moves down, and it keeps moving down, and it keeps moving down until it intersects with this blue line. And at this point, we can't decrease W2 any further, right? It's as small as it's going to get. It's at 0. And so if I were to push it down any further, it would start increasing a penalty, because now it's negative and that the absolute value. And then so at this point, the W1 coefficient just keeps shrinking. Okay, so it starts off here, and it forces W1 and W2 both to kind of shrink equally. All right, so we see it moving down in a diagonal line because it's penalizing both the W1 and the W2 equally until W2 can't be penalized anymore, and at this point it decreases W1 until it reaches 0, 0. And this is with lambda equals 500. Okay, what's going on with the contour lines? Okay, so the contour lines start off as this paraboloid thing, okay? But then as I increase my lambdas from 10 to 30 to 50 to 100 to whatever, we notice that our contour lines start forming these corners, okay? We start getting these weird corners going on here. All right, now why are we seeing that, okay? What we're seeing is this is the loss function if I add together the squared residual plus the penalty for the W's, okay? So this is the contour graph that I get when I'm adding the squared residuals and the penalty for the loss. So the original thing, when we're only looking at the squared residuals, we have these nice oval shapes, okay? And that makes sense because the squared function forms like a paraboloid, and we've got a, that's what we see, these elliptical shapes, okay? When I have a lambda like 150 or something like that, okay? What we see is that, you know, in this part, if you only focus, these parts look kind of a little bit elliptical, but what we see is that we get these harsh corners. And what's going on is that at this point, our W's incur some penalties, okay? We're adding in the penalty into here, and basically, if you think about what the penalty looks like for just an absolute value function, if you think of what the penalty looks like for an absolute value function, it looks like this, right? They're you know, 0, 2 has the same amount of penalty as 1, 1 as 2, 0, okay? And vice versa. Has the same amount of penalty as 1, negative 1, as 0, negative 2, as negative 1, negative 1, and negative 2, 0, okay? So you get these kind of this diamond shape where you're adding the absolute values. And basically, I'm having a cross between this absolute value penalty plus a you know, kind of this ellipsoid stuff, okay? And when we're adding the contour of the ellipsoids plus the contours of the absolute value function, you get this kind of this funny looking shape, okay? So I'm adding basically the contours of an ellipsoid to the contours that get created by an absolute value penalty here. Is that kind of okay? You don't have to, like, I'm not gonna like force you to draw anything like this or something crazy. Just, this is, I don't know, maybe it's helpful in illustrating this, maybe these plots are not, but that's what we have here. Okay, yeah, question.
So if we have lambda equals to 1, is L1 norm equals to L0 norm?
So if lambda equals 0, the lasso, the best fitting lasso values will be equal to the OLS. Okay. If lambda equals 1, then it will be slightly different. Okay. And your question was about the L0 and the L1 norms?
Yeah.
Yeah. So the L0 and the L1 norms are not going to be the same because for the L0 norm, if W is 10 or if W is 100, it incurs the same penalty of 1 or something, whatever it is, okay? But in the L1 norm, if W1 is 10 versus W1 is 100, those incur different amounts of penalty. Okay, so L0 and L1 norms will not be the same. All right, so this is a little bit of the exploration, and again, if you look at the path this blue dot traces out, as we increase the lambdas, it pushes things diagonally towards the origin, okay? It starts off by, because ultimately, you have no penalty when all your coefficients are 0, okay? But the way it penalizes both the W1 and the W2 is that they they first travel kind of towards the origin along a diagonal line. And then once it encounters one of the axes, it will go along this path, okay? So if, so the path that we see being traced out here is, you know, it starts here and it goes diagonal and then it goes down this path. If we started here, what do you think the path would be? It will also go diagonal and then it will crash down towards here, okay? And if it started, say, over here, then it will go diagonal and then it will go down. Does that kind of make sense? So it incurs penalties on all of our coefficients equally, kind of forcing them to move diagonally towards the origin until it hits one of the axes, and then it pushes them down to 0. Okay. And it also generalizes into higher dimensions there. Okay, so I think I write this. So as lambda increases, we saw the original optimal parameter values travel diagonally until it hits the x-axis and then is pulled towards 0. Okay, same thing, but now we're going to do the L2 penalty, which is taking the sum of the w's squared, of our coefficients squared. Not the absolute values, but the sum of the squared coefficients. Okay, so we have, it's the OLS loss plus lambda times the W2 norm. Okay, and so what we see here, this is something interesting, all right? So here I start with lambda equal to 10, and we're going to optimize these. So the OLS coefficients, again, are 1.458 and 0.453397, okay? As I increase my lambda, look what happens. This decreases from 1.45 to 1.249 to 0.92 to 0.74. But look what happens to x2, the coefficient for W2, or the coefficient for the x2 variable. It goes from 0.553, and then it goes up to 0.579, and up higher to 0.635, and then it starts to come down to 0.573, which is still larger than 0.453. And then it starts coming down again, okay? And so this goes to, as I've increased the lambda, this gets smaller, 0.457, 0.373, 0.272, okay? And at lambda 500, these just keep getting smaller. Okay. So, so what happens here, okay? See here again, I have these blue lines at 0, 0, okay? And then I also drew this line for when W1 is equal to W2, okay? And so again, the original estimates are at the red line. And what we will see, watch the path that the blue dot traces out, okay? It starts here, and then okay, it gets pulled towards 0, 0, and we never actually reach there with lambda equal to 1,000, okay? But what is this path that we get? It's a little it's a little bit different from parabolic, but yeah, we get this we get a curve, right? We get something that starts here, and it seems to kind of go like this, okay? So why would it travel towards this line of W1 equal to W2? So this is the line where W1 is equal to W2. So why would it do something like that? Okay, so just think of what the penalty is, right? The penalty is the W2 norm. I'm sorry, the L2 norm of W. Okay, L2 norm squared of W. And so if W is equal to something like 0, 10, okay, the penalty would be 100, right? Whereas if if it was 5, 5, this would have a penalty of what? 50, right? Okay, so it's preferable to have, as far as distributing 0, 10, it's preferable to have them kind of equal, okay? To have W1 and W2 equal each other gives a smaller penalty than when all of it is concentrated on one side, okay? Whereas if we look at the L1 norm, the penalty for both of these is 10. Absolute value of 0 plus the absolute value of 10 is 10. Absolute value of 5 plus the absolute value of 5 is 10. So both of these would incur the same penalty in the L1 norm, but for the L2 norm, 5, 5 incurs less of a penalty than 0, 10. And so we see this phenomenon where the when we use ridge regression in the L2 norm, it almost prefers to have the coefficients kind of distributed among all of the W's. Okay, and having them all kind of equal will minimize the kind of the penalty. And so if you look at the shape of the contour plot, you will notice that as I increase the lambda, okay, which means that the total error that gets incurred, as this lambda gets increased, we move away from, we're shifting our focus on the squared residuals to the focus on the penalty factor. And we will see that as lambda increases, the penalty factor that comes in is a circle, right? Okay, and so so you will see this going from an ellipse shape to more of, at this point it looks a lot like circles. Okay, we still have there's still a paraboloid aspect being added into it. Okay, so it's not perfect circles, but the lambda, the complexity penalty portion is circles, because that's what the L2 norm, how that function operates, because you're adding these squares of the coefficients. All right, we have a question.
Yeah, I'm trying to see it in the nicest way possible. What is the takeaway from these 30 minutes? It feels like, well, here's a formula. All right, well, here's what it does.
All right, well, let me stop you right there, because this question feels very disrespectful, and I don't appreciate that. Okay, maybe you'll allow me to just continue my lecture and finish my point, because what I'm teaching are these regularization methods that allow us to reduce the variance of our estimates by introducing a little bit of bias. And the way we introduce bias will be different whether we decide to use the L1 or the L2 norm, okay? All right, so here we're talking about the L2 norm, and with the L2 norm, the penalty that we are incurring, follows. So on the previous thing, when we were talking about the L1 norm, we said we had the contours for the L1 penalty were these diamond shapes. For the L2, the penalties look like concentric circles, okay? And so we've got these concentric circles, and we're adding in the ellipsoids, which are going to be centered somewhere around here. And as so this is the OLS part, and this is the W2 norm squared part, okay? And we're adding these together, and that's why we get kind of these shapes, where we get we start off with the ellipsoids, and we get something that differs and starts to look more like circles, okay? And so what we see is that when we do ridge regression, is that it's very rare for the coefficients to get pushed all the way down to 0, 0. Okay, that doesn't happen very often, but we do see this thing where it prefers to have the W1s and the W2s more equal to each other. Okay, and so that's why we saw this phenomenon where it traced out these paths. Okay, and so similarly, so we saw this kind of path being traced out. Okay. If we started off, say, somewhere up here, what do you think the path would be? Okay, So again, it's going to try to push things towards this this thing over here, okay? And if there's a diagonal line over here, we're gonna see something similar as well, okay? It's gonna kind of push things towards the path like that. Okay, yeah.
So I'm just curious. It's a curve till it hits the diagonal line, and then it's straight.
Yeah, it's a little bit more asymptotic. It doesn't actually hit the diagonal line perfectly, but once it gets close to it, you know, now we have this asymptotic, I don't know, approach down the diagonal line there. Okay. Okay, so what we see is that the contour lines look less elliptical and more circular. As lambda increases, the optimal parameter values travel towards the line W1 equals W2 and then gets pulled towards 0. Okay, and so what we get is the effect of the regularization of parameter estimates. Okay, and so what we will see, okay, this you're going to see a huge plot here. Okay. And what happens is that in each of these things, I'll try to do my best here, is that the true model, the true z, is 1.5, the true coefficient for W1 is 1.5, and the true coefficient for W2 is 0.5. Okay? These are the true coefficients. Now again, because of random noise, you might overestimate W1 to be 1.6 or underestimate it to be 1.45. You might overestimate W2 to be 0.6 or underestimate it to be 0.4 or something like that. And we saw that for, you know, our original example, our values just from OLS and our sample that we have, we got 1.458 and 0.4533, which is close to the true values of 1.5 and 0.5, but they are a little bit off. And we learned that in OLS, these are the best unbiased, meaning that when we do a whole bunch of these things, the average of all of them will be 1.5 and 0.5, but any individual sample and coefficients might have some variance, which is higher or lower, okay? And so what we will see is that the variance changes whether we're using the L1 or L2 penalty. And this is, so this is just the code that we ran, okay? And so these black dots represent the coefficient, the W1 and W2. And so we see there's quite a bit of variance for, in all of the, it's hard to see the black dot, but this whole cloud represents the different slope and, not slope and intercept, the different estimates for W1 and W2 that we can get. Okay, so the true is something around 1.5 and 0.5, but sometimes we get as low as, I don't know what this is, like 1, and as high as 1 or something, and sometimes way over here. Okay, and by introducing the lasso, the L1 penalty, what we see is that the way the penalty incurs things is it just kind of penalizes things equally. And so what it does is it just pushes the clouds diagonally down. Okay. But what we see is that once the cloud crashes into this x-axis, it zeroes them out, okay? And so the variance of this cloud is smaller than the variance of these clouds over here, okay? And so in a way, we are reducing our variance, okay? But more powerfully, as far as lasso goes, lasso can be used to perform variable selection. Okay, by pushing some of our coefficient estimates down to 0, we can say, well, let's just throw away W2. Let's throw away the x2 variable. Okay, it can push some of the coefficient estimates down to 0. And so we can use the lasso as a way to perform variable selection, variable subset selection, without needing to use your classical methods. The classical methods were things like forward subset selection, backwards or forward stepwise, I don't know, whatever you call these things, right? Forward and backward stepwise selection and things like that. And this can perform variable subset selection without needing to manually select them yourselves. So that's what lasso can do. Okay, so that's a very popular reason for using lasso, is that it can perform variable subset selection. What is this? Okay, this is what happens to the coefficient estimates when you use ridge regression. Okay, with ridge regression, we kind of see the same thing happen, where the cloud of points and all of the things, you can imagine tracing out the path from any one of these dots. Okay, if there's like 1,000 dots here, there's 1,000 dots in the red, 1,000 dots in orange, 1,000 dots in green, and 1,000 dots in blue. Okay, and they're all kind of traveling along this, whatever, this arch that approaches this line and follows down to 0. Okay, what we see here is that none of these variables get pushed to 0, so we cannot use this for variable subset selection. However, what does it do? If we look at the points that end up in the orange blob and the green blob and the blue dot blob and even the red blob, the variance of those blobs is smaller, right? So as we increase our lambdas, the variance of our coefficient estimates gets smaller. Okay, so what this is doing is, we know that the true values are 1.5 and 0.5. That we know that the true values are 1.5 and 0.5, but based on the random sample I get, it can be high as 2, and like it can be as extreme as like getting an estimate of 2, 0, or as off as like 1, 1, right? So you can get like this kind of wide variety of coefficient estimates for W1 and W2. Okay, and if you're displeased by kind of the wide range of values, then you can introduce a little bit of lambda, and now the range of values you get is a lot smaller. Okay, you're getting your estimates of the coefficients W1 and W2 are a lot more, what we might say, stable. Okay, they don't vary from each other as much. Okay, the problem though that you're introducing now is that the center of all the black dots is the true value of 1.5 and 0.5. The center of all the red dots is not the true value of 1.5 and 0.5. It's a little bit off. Okay, so we've introduced what we call bias, that the average of all of these things doesn't give us the true value of 1.5 and 0.5. It gives us something a little bit different. Okay, and as I increase my lambda, the variance of my estimates get even smaller, but also I end up getting farther and farther away from the true values of 1.5 and 0.5. I'm adding more and more bias into my estimates of W1 and W2. Yeah.
So where exactly is the balance? Like where do you say, okay, this is enough lambda in order for me to still preserve like a very close estimate to what the true coefficients are?
Yeah. So this is the tough question. Okay, where is the balance that we want, right? Obviously, we want the best estimates that are unbiased, and we want as little variance as possible. Okay, but this is the broader picture is known as the bias variance trade-off, and this is going to be something that comes up in other courses and things as well regarding these machine learning techniques and stuff. Is that which is a little bit more important? A little bit of stability, where a little bit more stability, but maybe it's not centered around the right thing, or would we prefer always to get something centered around the right thing, but we have a lot more variance in our things? And the answer is it's always going to depend on the situation. And ideally we want usually you kind of add the two together. You'll look at your bias and your bias squared and your variance, and you add them together, and you try to minimize the overall bias plus variance. And I think in 101C you'll see all of these curves and all of this stuff. But it's always a tough question to answer. So depends on the situation.
So is it always the case that when you add on the lambda, and then there will be more bias in there?
Yes, increasing lambda will increase the bias, okay? But increasing the lambda will also reduce the variance in your coefficient estimates.
Assuming the cloud like the lambda and the cloud's behavior in the curve like follow the trend, would the bias also follow the exact? Wouldn't the true mean move with the same exact?
No, the true mean is like we.
Sorry, I mean the bias, like the new like mean of the cloud.
Yeah. The mean of the cloud of this orange cloud is right here, and the mean of this green cloud is right here.
So it'll move with the exact same like trend as the cloud.
Yeah. So the true value is like right here. Okay, and so the bias is going to be kind of the square distance from here to here, and the bias of this is going to be the square distance from here to here, and the bias is the square distance from here to here, and the bias is the square distance from here to here. And so we can see that the bias of this cloud versus this cloud is a little bit less, and as we increase our lambdas, the bias, this distance, gets bigger and bigger. Okay.
But if you know it, can't you like kind of subtract it away?
Yeah, but you don't, is the thing. You can't. There's not like this bias compensation factor, right? You don't, because the point, the fact of the matter is you don't get to see 1,000 points in the cloud. You get one dot. Okay, so you get one dot. Let's say I give you this dot. Do you know that this is above the true value in W2 and less than the true value in W1? You don't. You don't know how it's related to W1 and W2 and the true values of W1 and W2. If I give you this dot, do you know where it is? You don't. Okay, so whether you get this dot or this dot, okay, because you have one sample of data, you don't know where the true value is. Of course, if we knew the true value, our life would be easy, right? But we don't know the true value. We get one sample of data, and it could be this dot, it could be this dot, it could be the dot right in the middle that we want, okay? But we don't know. And so when you have just this dot and no other information, you just have to say, well, overall, in the long run, it should average out to being the right thing, but I have no idea if I'm way bigger or way smaller, okay? And you also know that there's a lot of variance that goes in to this dot. It could be far away, it could be close, okay? Over here, if I give you one of the orange dots, right? If I tell you, I'm going to give you one of the random black dots here, and I'm going to ask you, how good are these estimates? You're going to have no idea if it's like really high or really low, okay? If I tell you I'm going to give you one of the orange dots, well, one thing is that you know it's going to be off from the true values by a certain amount. Like, there's bias introduced. But again,
within that smaller.
but it's within a smaller kind of cluster. And so that's kind of the trade-off. Would you rather know that you're off, but you're within this kind of quote safe circle, or would you rather know that you should be in the true thing, but like way off? So what do you want, right? So. Okay, I think this summarizes a lot of what I've said. Okay, so the L1 penalty seems to move the cloud of estimates closer to one of the axes. When the cloud bumps into the axis, the values zero out, and then until they all end up at 0, 0. And then the L2, oh yeah, on this thing, it's hard to see, but there's actually a whole bunch, there's just a bunch of blue dots right at 0, 0. So it went from black, orange, black, red, orange, green, and then blue. But by the time it got to blue, it was all 0, 0. So I did the same thing here. Okay, until they all end up at 0, 0, and then the L2 penalty moves the cloud of estimates towards this, and the variance shrinks. Okay. Let's keep talking about this. Okay, so here's kind of a quick quiz. Regularization modifies the loss function. OLS regression minimizes the mean squared error or sum of squared residuals. RSS only. Regularized loss function has the squared error plus a penalty for complexity or coefficients. Yeah. The fitted model will try to minimize both SE and complexity, and the lambda term is used to determine which goal has greater priority. Yeah, exactly. Okay, so those are your answers there. Okay, and this is what we covered. There's kind of, so we have the L1 and the L2 squared penalty. There's kind of a compromise called elastic net. and it has lambda, and it's a mixture of the L1 and the L2 squared penalty, and it's like weighted by alpha and 1 minus alpha, and this is what it has. So this is elastic net, and this is implemented in R, and you can use it. Okay, and this is kind of what it says. It says, it is known that the ridge penalty shrinks the coefficients of correlated predictors towards each other. Okay, that's what it means by kind of pushing it towards the line W1 equals W2, while the lasso tends to pick one of them and discards the other. So it picks one of these and throws away the others by pushing them to 0. The elastic net penalty mixes these two. If predictors are correlated in groups, alpha equal to 0.5. The alpha is how much we prioritize the L1 or the L2 penalty. Tends to select the groups in or out together. This is a higher level parameter, and we can try to push some of these things around, and you can kind of play around with these things. Okay, and again, lasso tends to push coefficients down to 0, can be used for variable selection. Okay, so I think this is just a bunch of code for using GLMnet on alpha, and so this was just an example from the data is the Chiro data set, and they were looking at peasant revolutions in Eastern Europe or something. I don't know. This is from like the 1930s. I don't quite know. It's a little strange to use the word peasant, but that's what it's called. All right. So they were looking at like different things and the intensity of the protests and I don't quite know. Okay, and I guess they looked at all of these other things. Yeah, I know, right? I don't even know what mid-peasant means, but we can look at some of these things, and we can graph how this stuff works. And I'm just going to kind of flip through these slides quickly. Oh, this plot got cut off. Okay. Well, anyway, what this shows in the plot that gets cut off, and I'm going to have to re-render this, is that the coefficients grow into a certain point and flatten out and things like this. This is, again, if you wanted to use, this is mostly just code if you wanted to use either lasso or ridge regression in R. On the previous slides, I did lasso and ridge regression kind of in this manual way where I'm using Optim and stuff like that. And you would not do this in real life, okay? GLMnet is a tried and true tested package that implements this very well. And so if you're interested in using lasso or ridge regression in R, read the documentation on GLMnet, and you can get your estimates this way, okay? And it allows you also to kind of mix, whether you want a mix of lasso and ridge regression or something like that, okay? So this is what, these are kinds of the things that we get. So anyway, I'm just gonna kind of skip through some of these slides here. I would say don't worry, stress too much about these ones regarding GLMnet. I'm not gonna throw this on a test or anything, okay? But it's just kind of there for illustration of the GLMnet package, which is how you would implement lasso or ridge regression. Yeah, question?
Well, speaking of this on the test, will all this stuff about L1 versus L2, like will something like that be on the test?
Yeah, I think that's fair to ask questions about that. Okay.
So I guess it returns to my earlier question, what does it all mean?
I don't, so again, how we introduce the complexity parameter penalty will have impact on how the coefficient estimates are determined, okay? So if you're using the L1 penalty, the lasso, the coefficients that get determined, some of the coefficients will get zeroed out, okay? And in such a way that when you get a coefficient that ends up being 0, that is doing variable selection for you, okay? The L2 penalty is ridge regression, and if you choose that, none of your coefficients will really get zeroed out. It's going to prefer pushing the coefficients towards one another, but will do it in such a way that reduces the overall variance of the coefficients. Okay, so your choice of whether you're using L1 or L2 will have a significant impact on the coefficients that get estimated. Okay. Okay, and so what we have here, as we mentioned earlier, is the bias variance trade-off. Okay, and so the bias variance trade-off says that, you know, ideally we have no bias and minimal variance, but that's often not possible, and so we have to kind of make a choice. All right, and the total expected prediction error means that is talking about, you know, here's your model that you trained, and you want to use your model to make predictions for future data. Okay, and you want your predictions to be as good as possible. You want the minimum number of the smallest error for your future predictions. You want your predictions as accurate as possible. Okay, and you can read the Wikipedia's page on the bias variance trade-off where they kind of derive this relationship. But it turns out that the total expected prediction error is going to be a combination of the squared bias, so how far off your coefficients are from the true values, okay, or the bias of the model, plus just the variance of the coefficients, because sometimes your coefficients are too big or too small depending on the random data set that you get, and just the squared error is just the error that exists in the population that you can't get rid of, right? So this is just error that naturally exists, okay? And the derivation's there. You don't have to worry about the derivation, okay? But this is the relationship. And a lot of times our models, at least with regularization, is in such a way that we can reduce the variance, but it's going to increase the bias, okay? Or we can keep the variance as it is, keep minimal bias, but we're going to have larger variance. Yeah.
So the sigma squared is usually also variance, right? Like with that.
So this is what we call the irreducible variance of the data points. Okay, this is the variance of your coefficients. Okay, so the coefficients themselves have variance, right? Depending on the random sample you have, your estimate of W1 and W2 might differ from someone else's estimates of W1 and W2 based on their random data. So the coefficients themselves have variance, and the coefficients that your model will produce might have a bias. Okay, OLS says your coefficients are unbiased. That if you took a random sample and found W1 and W2, and you took a random sample and found W1 and W2, and everybody took random samples and found W1 and W2, overall, if we average everyone's W1 and W2, those would all average out to be the true values of W1 and W2, which are unknown to us. Okay. OLS says that should be 0. The bias will be 0. Okay. When we do the ridge regression, when we do the lasso, the bias is no longer 0. It's going to end up, on average, a little bit off. Okay. But the advantage of lasso or ridge regression is that we're reducing the variance. When we look at your W1 and W2 and her W1 and W2 and his W1 and W2, the amount of variance that we see is a little bit different. This sigma squared is just variance that is not part of the model, is just variance that exists naturally, that people are different, right? This is something that we can't ever get rid of. This is just a fact that in life, everything's a little bit different. So the expected prediction error is going to be stuff based on our model and coefficients and whatever, plus just irreducible error that's out there. Okay, and so this is what we've got. We're looking at the expected value of the true relationship plus the random error. Okay, so this is the y's are the true relationship plus the random error minus the fitted values. That's our expected prediction error. Okay, the bias is the difference between the predicted value and the actual value, and then the variance is the variance of the predicted values. Okay. Standard deviation of the noise and the generated values. Okay. Yeah, so this is the variance of the predicted values and standard deviation is kind of the variance that just exists in the true process there. Okay. So here's just a side note illustrating the bias variance trade-off, okay? This is lowest regression, local regression. Do you guys see local regression in 101A? Some of you are nodding and some of you are shaking your heads. Okay. So local regression, are you guys familiar with like a moving average? So in a moving average, you just kind of like take the last 7 days and you average them, and you take the next 7 days and you average them, and you kind of do something like that. It's kind of like moving average regression. So you're going to take like the last, like kind of the 7 points and do like linear regression on these 7 points, and then you move over to the next 7 points and you take linear regression there, and take the next 7 points and you do linear regression there, and you kind of add all of these together. Yeah.
Yeah, I mean, you did the lowest line, right? You actually went over that in some version, but I don't think you called it local regression.
Okay, local regression, lowest. There, yeah, lowest is locally weighted something. All right. So that's what we have. Okay. So anyway, the result's not a mathematical function. It's technically found by taking the weighted regression of the values surrounding each x. And there's a smoothness parameter, okay? And you can say, I want a really smooth lowest line, or I'm okay with a really wiggly, jagged line, okay? And so this is, this red line represents the true model, okay? And what I'm going to do is I'm going to just generate some data points, okay? And so here is the true model, and I just generated some random data points in purple around the true model. So I took the true model, I added some random noise to the red line, okay? And by adding the random noise, we get these purple dots, and then I fit a straight line to those purple dots, okay? Here is another random set of data in orange, okay, generated around the red line, but I fit a straight line to these orange dots, okay? So it's just random points generated around the red line, but I'm just fitting a straight line to those, okay? And here's an, oh, what happened here? Okay, well, I did this 3 times, okay, and I'm hiding the dots, and we can see the different lines. So I did this, I guess I generated some blue dots and I didn't graph them, but I get a purple, an orange, and a blue line here, okay? Here is kind of the opposite, low bias, high variance. So I generate some random noise, random dots in gray around the orange line, and I fit a super wiggly line, okay? And here's another set of random dots generated around the true model of the red line, and I fit a wiggly purple line to kind of fit the data, okay? And if I graph both of these, we get 2 lines that are quite different from each other. Okay, so in this one, we get 2 models that do a very good job of fitting their current data. But again, if you take a look at these 2 models, they get quite, they're drastically different from each other. There's high variance, okay? If you took the average of these models, you'd probably get something close to the true model, okay? And so this just explains what I'm going to do. But I do this a whole bunch of times, and here's just a whole bunch of code here, okay? So again, this black line, the curve here represents the true model, okay? And there's like 100 little straight lines here, okay? Each of them was found by taking random noise around the true model, okay? We took random noise around the true model and we fit a straight line, okay? And then I did another set, random noise around the true model, and I fit a straight line. Another set, random true noise, fit a straight line to all of them, okay? And so these are all the different straight lines that I got. And these white dots here represent the average of all the different straight lines that I fit, Okay, and so what we see is that the white dots look quite different from the true model, which is the black line. Okay, so there's quite a bit of bias. Quite a bit of bias in that these white dots don't match the black line very well. However, if we ask, do these straight lines look a lot like each other? They do. Okay, the straight lines here, they look quite similar to each other. Like, I feel like I could just take a rubber band, a small rubber band, and just bind them all together, and it looks like, you know, I can just bundle up all the straight lines. There's low variance in terms of what the straight lines look like from each other. Okay. And so here's kind of just some calculations to kind of show what the bias is and the bias squared and all of this stuff. Okay. All right. What's going on over here? Okay. This one is almost like impossible to see. So the idea here is, again, there's a true model, this black line here, okay, and I've generated random noise around it. Okay, so I generated random noise around the black line, and I fit like one of these lines to the random data points. Okay, and then I generated more random data points around the true black line, and I fit another wiggly line. Okay, and so what we get is this huge crazy spaghetti mess. Okay, and every single one of these individual lines look crazy, and they're like very different from each other. Okay, like this one goes up and this one's going down and this one's going up and this one's going down. There's high variance between one fit and another fit. Okay, we've got high variance there. However, if I take all of these spaghetti lines and I just take the average of them, okay, so if I take all of what the spaghetti lines predict and I take the average, I get this white dot. Okay, and what we see is that the average of these white dots follow the black line very closely. It's not perfect. Like this white dot's a little bit lower than the black line, and this white dot is a little bit higher than the black line. Okay, but these are just the average of what these different kind of spaghetti-looking things predict. So I fit like 100 of these different wiggly lines, and I took the average of them. The average of those are these white dots, and what we see is that the difference between the white dots and the black line, the true model, is there's very little difference. Okay, so and here we would say there's low bias. Low bias because the average in the long run ends up very close to the true model. But any one of these lines is wild and all over the place, and there's a high amount of variance from one squiggly line to another squiggly line. Okay, so this is high variance, low bias, and over here is low variance because all these lines almost look alike, but high bias because the white dots don't really follow the black line there. Okay, and generally we want something that's kind of somewhere in between. Is that okay? What's going on? What this plot illustrates and what this plot illustrates. Okay, these slides in between with all of these numbers, I was like getting a little overzealous to try to show that the relationship between bias squared plus variance and all of this adds up together. You can look at it. It's like, you know, you work so hard on something and you're excited, and then like a couple days later you look at it and you're like, that was a lot of work for not a whole lot of payoff. But so anyway, that's what these slides are. You can look over them and appreciate my hard work, or just say he said it wasn't that important, so don't worry about it. But okay, but you know, all of these calculations here, that's what we've got there. Okay, so is there a balance that we can arrive at between the two extremes? Maybe, I think, I don't think I created a plot here, but we can kind of see. You know, we can reduce the variance, eliminate the bias, and things like that. Okay, how are we feeling?
Good.
All right, well, I got one good from the front row, so I'll take that. Okay, we are going to shift gears entirely, okay? So, all right, so before I move on, let's just kind of pause and before I get even into the gradient descent. Okay, so what we've talked about so far there was a lot we've covered, right? So we saw matrix notation for ordinary least squares regression. We talked about, today we talked about regularization. But prior to that, we also talked about gradient descent as a way to minimize some kind of objective function. Okay, so we have an objective function that we want to minimize. And so what we are going to do now is we are going to apply what we learned about gradient descent to a new application. So far we've just been applying it to ordinary least squares regression, which is great. Like multiple linear regression, if you can do that well, like that's a very, very powerful tool. It's not like there's no buzzwords around it, okay? It's not, I guess it's not as impressive to put on a resume. However, in real life, it's very useful. If you can do multiple linear regression from your 101A class, and if you can do it well, that's great, okay? I guess what we'll do today is I'm going to introduce kind of one of those buzzword ideas, but it's actually also very useful. And we will cover the most basic form of a neural network, okay? So I'm going to introduce neural networks here, and we will cover just the most basic form, okay? There's a lot of stuff going on out there with deep learning, and there's like packages that run in R and Python that can set up all of these deep neural networks and do all sorts of cool stuff. You can even like just take like a short little course on Udemy or whatever it is and do like deep learning. But it's kind of like, I don't know. I don't know if I agree with this philosophy of just like teach somebody how to click some buttons on the computer and call themselves a data scientist. I don't know. All right. But at least I hope you'll take in a little bit of stats background here. And this is an application of gradient descent, because the way we train neural networks is gradient descent, which is that simple algorithm, which is what? We look at the hill, we look which way is uphill, and then we take a step downhill, okay? And we just say, keep walking downhill, and eventually you should reach the bottom, okay? Now, you run into problems if the surface is really wobbly, okay? And there's like a bunch of minimums. The instructions only go downhill will just get you most likely to just a local minimum and not necessarily the global minimum. But we won't worry too much about that, okay? So what we're going to do is we're going to basically use the same thing that we always did with gradient descent, except we just make our model a little bit more complicated, okay? So we want to find the values of W that's going to minimize some function f, okay? Which in our case is usually our cost function, our loss function, whatever we call it, okay? Gradient descent's an iterative algorithm, and we start at some location. How do we select our next location? We just walk downhill, right? Okay. So we say the next iteration, if we're currently at W at time n, then W at time n plus 1 is just our current W minus, we take the step downhill. The gradient points uphill, we subtract that, so we're taking a step downhill. And it's tempered by our learning rate, okay? So that we're not taking steps that are too big. All right, so we will introduce, I will introduce neural networks. There's a bunch of videos out on YouTube about neural networks because apparently you say neural network and everybody gets excited. And so there's a bunch of YouTube places out there with neural networks. I think these two are the best, okay? Watch the Welch Labs playlist on neural networks. It's a couple years old, but it's excellent. And I've based a lot of my lectures on this series of videos, okay? So just watch through this playlist of videos, okay? And then there's this other guy, 3 Blue 1 Brown, and he created a playlist on neural networks, which is also very good. And 3 Blue 1 Brown, well, and also Watch Labs, both of them they're great channels that you should subscribe to, okay? And watch all of their videos. I think I already forced you to watch 3 Blue 1 Brown's linear algebra videos, and do we like those?
Yeah.
Kind of? Okay, so those of you who watched. Okay, and so we're just going to explore the simplest kind of neural network. This is going to be like a 3-layer or single hidden layer neural network. This is the simplest of its kind. They've actually been around for a long time, but they are very computationally expensive, and so only recently, with our computational power of like GPUs and stuff, have we really been able to implement these kind of at higher levels. Okay, and pretty much neural networks power a ton of AI type of things. Okay, so all of your picture recognition things. I don't know. You guys are young, so I don't know if you remember when speech recognition on your phone became like a viable way to text people and send messages. Like, that was a huge breakthrough, because for a long time, anytime we did speech recognition, it sucked. Okay, it was terrible. It was very buggy. So speech recognition. Now you can, like, when you take pictures and you put it on Facebook, Facebook automatically draws boxes around faces and says, "Is this person?" And when it first started doing that, people were freaked out because it was super creepy, right? But now it's like totally normal, and
Still creepy.
okay, well, yeah, and then they're gonna sell it to some Russian company. Okay, but so anyway, this is what we have. It's a wild world out there. Okay, it's like the AI Wild West, depending where you are. Okay, but anyway, we get to use gradient descent. It's an excuse to use gradient descent in an application that is kind of neat. Okay. All right, so in a simple sense, all it is it's a function. A neural network, you take some inputs, you do some stuff to it, and it produces an output, okay? All right, that's what every other function in math does. You put something in, it does something to it, it spits something out. And that's all a neural network is, okay? You take an input, you do stuff to it, spits it out, all right? The inspiration of it is like how the neurons in your brain are connected. It's a very loose inspiration, because the more we study neuroscience, like, there's certain things that are similar, but then there's also things that are like quite different. Okay. So anyway, each node does a little thing. Okay. So this is where we're going to start. Okay. We're going to start with an X and our output Y. All right. And this is just a very, very, very simple data set. And our X represents 2 variables: how many hours of sleep we got and how many hours we spent studying, okay? And we're going to try to predict the exam score. And we've got 3 observations. So one day we slept for 10 hours, studied for 2 hours, and we got a 93. Over here we slept 5 hours and studied 1 hour, and we got an 82. And when I studied for 5 hours, but I only slept 3, I got a 75 or something like that, okay? This is made up. But it does say sleep is important, right? So anyway, if you take away one thing from our class, sleep a lot, okay? It's our first line of defense against mental exhaustion, okay? Okay, and so this is so the neural network looks like this. You've got an input layer, a hidden layer, and an output layer, okay? It all starts with an input layer, ends with an output layer, okay? And so because our X matrix has 2 columns, it has 2 variables, our input layer will have 2 nodes, 1 node for each variable, okay? And then the output layer has 1 variable, because we're just trying to predict exam score. Now you could have a different neural network where you're trying to predict like 10 different things. Okay, then your output layer will have 10 different outputs. Okay. A neural network will also have some hidden layers. Okay, and in our class, we're just going to have one hidden layer, and in our hidden layer, we'll have 3 nodes. Okay, that's an arbitrary choice. Okay, how many nodes you want in your hidden layer is arbitrary, but I'm going to put 3 to just kind of keep things simple. Okay. If you hear about deep learning, it's basically the same thing with a neural network, except instead of 1 hidden layer, you might have like 100 hidden layers, okay? And by having 100, we're saying there's a deep number of layers, okay? By having lots of layers, make it deep, okay? So this is what our picture looks like, okay? Hours of sleep, 2 nodes. In the hidden layer, we've got 3 nodes. And the output layer, we've got 1 node. Okay, and each of these nodes, every node is connected to all the nodes in the next layer. Okay, so x1 is connected to all 3 nodes in the hidden layer. X2 is connected to all 3 nodes in the hidden layer, and every node in the hidden layer is connected to all the nodes in the output layer, which is only 1. There's only 1 node in the output layer, so they all form a connection. But if we had multiple nodes in the output layer, every single node in the hidden layer would be connected to every node in the next layer. Okay. This is okay for this picture? Okay. So again, you can have over 100 layers, and we call that a deep neural network. And the ImageNet data set has done this, and this is, we'll watch this video because this is cool. Has nothing to do with what we're learning other than it uses a neural network. Okay. But basically, this is a real-time, well, not the commercial, but it's a real-time usage of a neural network. And basically, it's a car driving down the street, and it's identifying things that it sees. Okay, and so it's putting blobs around what it identifies as other vehicles. And it says this is a car with 97% certainty. This is a car with something. This thing is over here, a person with 99% certainty, a person with 98% certainty. This is something else like a train or something. A traffic light, it's identifying out there and stuff like that. Okay, you can sit and watch this drive along the highway. All right, so anyway, this is really what's powering our, when self-driving cars, well, self-driving cars are being tested and whatnot already, but pretty much all of that stuff is powered by neural networks. We're not going to get to do anything cool like that, okay? Just temper your hopes, all right? We're doing 2 columns of input and 1 output, all right? Okay? We don't get to do cool stuff yet. But the deep stuff, you know, with these high-powered neural networks can power all sorts of cool stuff, okay? The thing about the neural network, though, is it's like the opposite of linear regression in that there is no interpretability, okay? Or very little interpretability. I shouldn't say no interpretability. It's kind of like neuroscience. Does anyone know how our brain works? Not really, right? Like we have neuroscience and we're like, okay, I think this part's responsible for long-term memory and this part's responsible for like vision and stuff. And we kind of have some notion a little bit of how the brain works. But again, it's really complicated. And similarly, for neural networks that have hundreds of layers, like we're not quite sure what this layer does. Okay, what is this layer responsible for? What is this node responsible for? We don't really know. We're just like, it does something, okay? So anyway, this is where we are. So we're not really going to know what these nodes do, and you're going to get coefficients, and we're not going to have any idea what these coefficients mean, okay? But let's talk about the coefficients that exist, okay? The coefficients are going to be basically the weights that we will apply to each of these arrows. Oops. Okay, so each node is connected to, each node in this layer is connected to the node in the next layer, and we can change how strong this node affects this node by changing the weight applied on these arrows. Okay, so how many weights are there in our neural network? Okay, we've got 6 here because we've got 2 over here and 3 over here, so we've got 6 connections here. 1, 2, 3, 4, 5, 6, and we've got 3 connections here. So we're going to have 9 coefficients to figure out. Okay, so we've got 6 connections here and 3 connections there. Each one has a weight. And training the neural network is figuring out what these weights should be. That's what training the neural network is all about. Okay, so I've labeled all of these weights. Okay, so this one, we've got 2 weight matrices. The weights between the input layer and the hidden layer, and the weights between the hidden layer and the output layer. So this is weight matrix 1, which is the W super 1. And over here we've got weight matrix 2, which is the W super 2. Okay? And this is W11. This is the weight from node 1 to node 1. And this is W21. It's the weight from node 2 to node 1. And this one's W12. It's the weight from node 1 to node 2. And this is W22. It's the weight from node 2 to node 2. Okay? So that's kind of how I've labeled these. And I put these ones in blue, and these ones in purple, and these ones in red. And these ones are W11 because it goes from node 1 to node 1. This is 2-1 because it goes from node 2 to node 1, and 3-1 because it goes from node 3 to node 1. Okay? But they're all super 2. So if I arrange these in matrix form, I get this. Okay? W11, W super 1, which has W11, 1, 2, 1, 3, 2, 1, 2, 2, and 2, 3, and then W super 2, which has W11, W21, and W31. Is this okay? The labeling of the weights. Okay, and so what I'm going to do is we take our inputs x, and we're going to multiply them by our w's. Okay? So x is n by 2, right? It has n observations in 2 columns, and w super 1 is 2 by 3. It's got 2 input, 2 rows, and 3 columns. Okay? So x is n by 2, w super 1 is 2 by 3. So this will output to n by 3. Okay? And if I do all the multiplication, we get this. Okay? This is just one value. You're adding x1, w11 plus x12 and w21. But this is one value, and this is one value, and this is one value. And so we're going to get n rows and 3 columns. All right? So I always find it helpful to write underneath what the dimensions of each of these things are. Okay, so I got n by 2 and 2 by 3, and that's going to result in an n by 3 matrix. Okay, and so Z is an n by 3 matrix. And what we will do is we apply a function to Z. Okay, so the function could just be as simple as the identity function. Okay, in our neural network, we're going to use what we call a sigmoid function, which is basically like the logistic function. And so we just take our n by 3 matrix, and element-wise, we will apply a function to it. We're going to apply a function to each element in the n by 3 matrix, and so we're going to get an n by 3 matrix as an output, because we're just applying a function to each element. Okay, and so the function we apply is the sigmoid activation function, which is this 1 plus 1 plus e to 1 over 1 plus e to the minus t. But it's just a function, okay? It just takes an input, does something to it, okay? And we call this, the output of that, we call it A, because it will be like the node has been activated, all right? So if you're thinking of like a neuron, depending on the electric signal that comes in, it like activates the neuron, which will either send out another pulse or something, right? When I think about the brain, I always think about free will. Do you guys think we have free will? Okay. Because if you talk to some neuroscientists, they're going to say we don't have free will, that we're just the result of electrical impulses happening And if we knew exactly what impulses come in, we can predict what someone's going to do. And maybe that's true. I like to believe that we have free will, that we're given a spirit and a soul, that we have, we're responsible for our own actions, and we're not just, but anyway, it doesn't matter. Like, the words that are coming out of my mouth is just the result of electrical impulses that are happening. It's too crazy to think about, but okay. Anyway, so this is the sigmoid activation function. We put in something, and it does something to it, and it spits it out. This is what it looks like. It's the logistic function. So basically, big values get turned into 1. Really negative values get turned into 0, okay? And then if you plug in 0, you get 0.5, right? So if t is like 1,000,000, okay, this you get 1 over 1 plus 0, which is 1, okay? And if t is like negative 1,000,000,000, okay, it's going to get 1 over 1 plus infinity, and you get 0. And if you plug in 0 here, you're going to get 1 plus 1 over 2, or 1 over 2, and you're going to get 0.5, and then you get something in between, okay? There's a bunch of different activation functions, okay? Sigmoid activation function has fallen out of favor recently, and we prefer the rectified linear unit. It doesn't matter, okay? We're going to just continue using this. Okay, so this is what we have. We've labeled this, okay? So we've done x times w, and we get z. We've applied the activation function to z, and we get a. So z is n by 3, right? We've got 3 nodes. Z is n by 3. We activate them with the function, and we have a, which is n by 3. So we're going to multiply a, which is an n by 3 matrix, times w2, w super 2, which is 3 by 1. Okay? And so what will the dimensions of the result be? It's going to be n by 1. All right? So when you multiply this out, they all kind of combine, and you get an n by 1 column matrix. And then we apply the activation function there, and we get y hats. All right, so to summarize, this is what happens. Our input matrix, n observations, 2 columns. We multiply that by our first weight matrix, which is 2 by 3. And so this will become n by 3. We apply a function, n by 3, and we get n by 3. And then we take that result, a2, and we multiply it by w2, and we get n by 1. And then we apply a function there, and this is our y hat. Okay? So if I want to write y hat as just some nested functions, we can do that, okay? It's x times w1 applied to a function, take that result, multiply by w2, and apply a function there, okay? So y hat is just really just the result of this kind of function. Okay, we plug in our x, we've got some w matrices, we multiply, apply functions, multiply, apply functions, and we get our results y hat. Yeah.
So what exactly is a layer?
What is a layer? It's just a series of nodes, okay? All it is we're just taking some values, we're going to just multiply it really by a matrix, and we get like another matrix of another dimensions, and we're going to call each of those things a node in the next layer.
Okay.
Yeah.
Is this a layer that we have displayed on screen?
No, this is the output y hat, and this is the summary of the operations that we're doing, okay? So we have the x's are input values in our input node, or input layer. We multiply it by some weights, and we get the value z, which are technically the values in the hidden layer. We apply some functions to those values, and we get another set of values a. All right, so these are values in our hidden layer. We multiply them by another matrix w, and we get values at our next layer z3, z super 3. And then we apply a function, and we get our predicted values. I'm sorry?
So each equation is a layer?
Just, I'm not sure what you mean by each equation is a layer, okay? So there's 3 layers here, right? It's kind of each column of nodes here as a layer. So we're saying we got input values, and we multiply our input values by some weights, and that produces our values that go into the next layer. Okay, and then at the next layer of nodes, we apply a function, and they produce some output values, and we take those output values, we multiply them by w's, and they kind of create our input for our final layer here. Okay, and so that's what we have. But again, there's not a bunch of interpretability here. Like, if you wanted to know what does this represent or what does this do, there's not a whole lot of meaning. It's kind of asking what exactly is this particular neuron doing in your brain, and it's hard to say, okay? We kind of have general ideas and say, like, this part of the brain's responsible for, I don't know, something, right? And that's what your psychology courses are for. But we really don't know, okay? And similarly, for computer neural networks, we don't really know. Somebody's hypothesized and said that maybe one day we will have neuroscience classes for computer neural networks, which, I don't know. Yeah, it's possible, right? Like, we're going to try to understand the algorithm that happens inside the self-driving car and figure out which nodes are responsible for recognizing what's a car and what's a human and stuff like that, okay? This follows very closely what the videos are doing in the Welch Labs videos. They don't include bias terms, and bias terms add a constant for these things. And in your, not this coming home, like I've released a second homework assignment, but in your third homework assignment, when you work on neural networks, part of your homework will be to figure out these bias terms and how they interact with stuff, okay? So it's a challenge, that aspect, okay? And I'm forcing you to work on them, okay? And so if we wanted to include bias terms, we would add a constant to each of these things. To each of these nodes, there's a little, but somehow this picture keeps getting cut off, and then we're adding a constant here. And this is what it looks like, okay? And so, so if we wanted to do bias terms, we take our x and we multiply it by our w, okay? N by 2 and 2 by 3. And then the bias, okay, we're using the same bias for each of our z nodes, okay? And in order to kind of get everything to line up, you have to multiply it by some matrix. And here we're going to call it J, which is an n by 1 matrix, which is just a column of ones, okay, to kind of duplicate what the bias terms are, okay? And so this will become an n by 3 thing, and I can add these together to get this z here, okay? So J is just a column of ones that will duplicate this. The bias is 3 by 1, but I'm going to transpose it, so it's 1 by 3. And so so if you think of if B1 is equal to B1, B2, B3, when I transpose it, it's going to be B1, B2, B3, and I'm going to multiply it by this, okay? And this will become B1, B2, B3, B1, B2, B3, dot, 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 B1, dot, 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 B2, dot, 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 B3. Now that I've written this on the screen, I think I actually typed this up. Okay. Yeah, exactly. Okay. So we do this, okay? So here's our B1, B2, B3. Okay, and then we multiply them out, and then they all combine. Okay, and so this ends up being n by 3. And then we do the same thing. We take this whole thing and we run it through the function f, okay, and we get our a's, and then we do our a's times this, and we multiply it. We add j times b2, which is just 1 by 1, and so this gets added on like this, and we get an n by 1, and we run that through our function there. Okay, so if we include our bias terms, this is what it looks like, okay? XW, so this looks really crazy and scary, but all we're doing is we're just taking a matrix X, multiplying it by weights, adding some constants, applying a function, and we just kind of repeat the process for each layer. And we only have a total of 3 layers, and so just the function gets applied twice. Okay, so this is how we get our prediction values, and this is what we call the forward feed algorithm of the neural network. Okay, it sounds scarier than it is. We're just applying the operations in order. Okay, but this is how we get our predictions based on our inputs and our weights and bias values. Okay, and so what we need to do now is we need to measure how good or bad our predictions are. Okay, so we got our predictions y hat, and we're going to compare our predictions y hat to the actual values y. So we're going to do y minus y hat, and then we'll square that difference and add them up. Okay, so we're just going to do the sum of squared errors, and so this is our loss function. Okay, y minus y hat squared, and so in matrix form, this can just be y minus y hat transpose y minus y hat. Is that good? Oh, what did I write? Next class. Okay, so so what we will do next, okay, so now we have a loss, and then so the next thing we're going to do, and the next part is, it's like the scariest and hardest part of neural networks, and we're going to work through it, is we're going to take the gradient of this, okay? We're going to take the gradient of the loss function so that we can do gradient descent, okay? So how do we take the gradient? What is the gradient? It's basically the derivative, right? It's basically the multidimensional derivative, okay? Except our function is y minus y hat, and what is y hat? Y hat is, what do you call this? Sigmoid function or a logistic function applied to logistic function applied to a product of matrices and stuff like that, okay? So, and then this is y hat, and it's inside basically y minus y hat transpose times y minus y hat. So it's a little bit messy. It's going to be a little bit messy, and we do weird stuff as far as taking derivatives and gradients with respect to matrices and vectors, and so it's gonna get a little bit messy, but we'll do it, okay? And I feel like my notes are fairly thorough, and so please be sure you kind of review them after class, and we'll do that, and then we'll apply it, and we'll try out to see if we can do get our neural network to recognize some stuff there. All right, we'll end class here for now, and we'll see you guys on Wednesday.